Hello everyone, and welcome back to the AI Academy's course on ethical hacking. In our last session, we explored the fundamentals of IPv6, diving into its features, expanded address space, and why it's a critical upgrade from IPv4. We also touched on IPv6 routing protocols like ripping and OSPF v3. Today, we'll discuss advanced routing concepts, including multi-area OSPF for scalability, policy-based routing for smarter traffic management, and techniques like route redistribution for interoperability. So, let's dive in and continue building your networking expertise. Let's start by understanding why routing is critical in network communication. In today's interconnected world, data travels across complex networks to reach its destination. These networks are often made up of multiple interconnected devices, such as computers, servers, routers, and switches. The job of routing is to determine the best path for data to travel across this intricate web of devices. Think of routing as the postal system of the Internet. Just as postal services figure out the best way to deliver letters and packages from one address to another, routers ensure that packets of data reach the correct destination efficiently and reliably. Without routing, there would be no structured way to send data between devices on different networks. For example, when you stream a video, routing ensures that video packets are delivered in the right sequence and at the right speed. When you email someone, it's routing that ensures your message travels across servers and reaches the intended recipient. In essence, routing is the backbone of network communication. It ensures that data is delivered correctly, securely, and as efficiently as possible. To understand routing better, we must delve into packet delivery methods. A packet is a unit of data that is transmitted over a network. For efficient communication, large pieces of data are broken down into smaller packets that travel independently to the destination and are reassembled there. Now, how these packets are delivered depends on the network layout, and there are two primary methods: direct delivery and indirect delivery. The direct delivery happens when the source and destination are part of the same physical or logical network. This means there's no need for the packet to pass through a router. Instead, the data is transmitted directly to the destination device. For instance, devices connected within the same local area network can use direct delivery. A laptop printing to a printer on the same Wi-Fi network utilizes direct delivery. In this case, the sender identifies the recipient using the MAC address, a unique identifier associated with the network interface. In the indirect delivery occurs when the source and destination are on different networks. Here, the packet must traverse one or more routers before reaching its final destination. Routers act as intermediaries, directing the packets based on the best available path. For example, accessing a website hosted in another country involves indirect delivery. A video call between participants in different locations also relies on indirect delivery. In indirect delivery, routers play a pivotal role in deciding the path packets will take. They analyze the destination IP address in the packet and consult their routing tables to determine where to send it next. Now, let's discuss how routers function and their role in the OSI model, specifically at Layer 3, the network layer. The OSI model divides networking into 7 layers, each with a specific role. The network layer is responsible for routing, which includes determining how data is forwarded across networks and ensuring it reaches its destination. Routers operate exclusively at this layer, and their main responsibilities include addressing. Routers use IP addresses to identify devices on different networks. Routing. They determine the best path for packets to travel based on their destination IP addresses. Fragmentation. If a packet is too large for a network segment, routers fragment it into smaller packets and reassemble it later. At Layer 3, routers use routing protocols such as RIP, OSPF, and BGP to share information about network topology and determine optimal paths for data flow. This ensures efficient communication across diverse and interconnected networks. Imagine you're traveling from one city to another. The router is like a series of traffic signs and maps, guiding your packets along the best roads to avoid congestion and ensure timely arrival. Routing is only possible because routers maintain a routing table, a database that lists all known routes to various destinations. Let's break down the components of a routing table and understand its importance. Key fields in a routing table. A routing table contains multiple entries, each representing a possible route for data packets. The most crucial fields include destination. This specifies the IP address or range of addresses, subnet, for the route. For example, if the destination is 192.168.1.0/24, this entry will handle all packets destined for devices in that subnet. Subnet mask. The subnet mask defines which portion of the IP address identifies the network and which portion identifies the host. It works in tandem with the destination field to pinpoint the intended network. For instance, a subnet mask of 255.255.255.0 implies that the first three octets, 192.168.1, identify the network, and the last octet represents individual devices. Next hop address. This is the IP address of the next device, usually another router, to which the packet should be forwarded. If the destination is within the same network, the next hop address might be the destination device itself. Otherwise, it's the address of the next router in the path. Together, these fields allow routers to make accurate forwarding decisions, ensuring packets reach the correct destination. Flags and metrics. Routing tables also include flags and metrics to provide additional information about each route. The flags indicate the status or characteristics of a route. Common flags include U, up indicates that the route is active and reachable. G, gateway specifies that the route leads to a gateway, a device that connects different networks. H, host specific indicates a route specifically for a single IP address, rather than an entire subnet. Metrics. The metrics measure the cost or efficiency of a route. They help routers decide between multiple possible routes to the same destination. Common metrics include hop count, the number of routers a packet must traverse to reach its destination. Bandwidth, the maximum data rate of the path. Delay, the time it takes for a packet to travel the path. For example, if there are two routes to the same destination, one with a hop count of 2 and another with a hop count of 4, the router will prefer the first route. Routing tables are the brains behind a router's operations. Without them, routers would have no way of knowing where to send packets. They are dynamically updated by routing protocols, ensuring that they reflect the current state of the network. For instance, if a link goes down, routing protocols like OSPF automatically adjust the routing table to find an alternate path. Similarly, if a new device joins the network, the table updates to include routes to the new device. In summary, routing tables are critical to the functioning of modern networks, enabling seamless data transfer even in the face of network changes. Let's now discuss about static and dynamic routing. The static routing is the simplest form of routing, where routes are manually configured and maintained by a network administrator. It involves explicitly specifying the path that packets should follow to reach their destination. A static route is essentially a rule that tells the router, for any packet destined for a specific network or host, send it to a particular next hop address. For example, suppose you have a router with an interface connected to 192.168.1.0/24 and another interface connected to 10.0.0.0/24. To send packets to the 10.0.0.0/24 network, you can define a static route that specifies the interface or next hop IP address. Practical applications of static routing are that they are useful for small networks. Static routing is ideal for small or simple networks where the routes are straightforward and rarely change. For instance, in a small office LAN with 1 or 2 routers, manually configuring routes is manageable. Stub networks. A stub network has only one route in or out. Static routing works well here because there's no alternative path to consider. Backup routes. Administrators sometimes use static routes as backup or failover routes. If a dynamic routing protocol fails, the router can fall back to a predefined static route. Security-critical environments. Static routes offer more control, making them suitable for networks that require tightly controlled traffic flow, such as in military or financial systems. The static routing has several benefits that make it appealing in certain scenarios. Simplicity. Static routing is easy to understand and implement, especially in small networks. Low resource usage. Since static routes do not rely on routing protocols, they consume minimal CPU, memory, and bandwidth. Predictability. With static routing, the paths are explicitly defined, making the behavior of the network predictable. Enhanced security. By controlling the exact routes, administrators can restrict traffic from taking unintended paths, reducing exposure to potential vulnerabilities. Despite its simplicity, static routing has significant limitations such as manual configuration. Any change in the network topology requires manual updates to the routing tables. This is labor-intensive and error-prone, particularly in large networks. Lack of scalability. Static routing is impractical for complex or dynamically changing networks. Adding or removing a route requires reconfiguration on multiple routers. No automatic failover. If a link goes down, the router cannot automatically find an alternate path. Manual intervention is required to restore connectivity. Limited flexibility. Static routes do not adapt to changing network conditions, such as congestion or outages. In summary, static routing is effective for small, stable networks or specific use cases like backup and security. However, its lack of scalability and adaptability makes it unsuitable for larger, dynamic environments. The dynamic routing automates the process of discovering and maintaining routes using routing protocols. Unlike static routing, which requires manual configuration, dynamic routing enables routers to exchange information about network topology and automatically adjust to changes. Dynamic routing protocols, such as RIP, OSPF, and BGP, handle tasks like discovering routes. Routers use dynamic protocols to learn about other routers and networks in the topology. Updating routing tables. When the network changes, like a link goes down or a new route becomes available, dynamic protocols update routing tables automatically. Adapting to failures. Dynamic routing can detect failures and find alternative paths without human intervention. Dynamic routing is particularly beneficial for medium to large networks where manual route management is impractical. Let's explore its key features. Scalability. Dynamic routing supports large and complex networks by automating the addition and removal of routes. As new networks or devices are added, routers dynamically learn and adjust their tables, eliminating the need for manual configuration. Adaptability. Dynamic routing protocols continuously monitor the network and adapt to changes, such as link failures, network congestion. For example, if a link fails, OSPF can quickly recalculate the shortest path and reroute traffic. Fault tolerance. Dynamic routing protocols can reroute traffic automatically when a path becomes unavailable, ensuring minimal disruption to services. Efficient use of resources. Dynamic routing minimizes administrative overhead by automating route discovery and management. Protocols like BGP can optimize routes based on policies or performance metrics such as latency. Static and dynamic routing each serve distinct purposes in network design. Static routing provides simplicity, security, and predictability, making it suitable for small or fixed networks. On the other hand, dynamic routing is indispensable in larger, complex networks that require scalability, adaptability, and fault tolerance. Understanding the strengths and weaknesses of both approaches allows network administrators to make informed decisions based on the specific needs of their infrastructure. In most real-world scenarios, a combination of static and dynamic routing, leveraging the strengths of both, is used to achieve optimal network performance and reliability. Routing protocols are broadly classified into two categories based on the scope of their operation, such as interior gateway protocols, IGPs, and exterior gateway protocols, EGPs. The interior gateway protocols operate within a single autonomous system, which is a network or group of networks under a single administrative domain. The examples include RIP, OSPF, and EIGRP. The IGPs are designed to optimize routing within an organization, ensuring efficient communication between routers. The exterior gateway protocols operates between different autonomous systems and are used for inter-AS communication. They manage routing across the Internet, where diverse policies and preferences must be accommodated. BGP, Border Gateway Protocol, is the primary example of an EGP. It's vital for Internet routing and ensures that data can traverse multiple AS. The protocols are also categorized based on the method they use to discover and maintain routes, such as distance vector, link state, and hybrid protocols. The distance vector protocols use simple metrics, like hop count, to determine the best path. Routers share entire routing tables periodically with their neighbors. Examples: RIP and RIPNG. Strengths: simplicity. Weaknesses: slow convergence and susceptibility to routing loops. The link state protocols. Routers share information about their immediate neighbors and build a complete map of the network. Each router independently calculates the best path using algorithms like Dijkstra's. Examples: OSPF and OSPF v3. Strengths: scalability, faster convergence. Weaknesses: higher complexity and resource usage. And lastly, the hybrid protocols. Combine elements of both distance vector and link state protocols. Offer faster convergence and efficiency while maintaining simpler configurations. Example: EIGRP. Strengths: balances simplicity and scalability. The first one is RIP, the Routing Information Protocol. It is a distance vector routing with hop count as metric. RIP is one of the earliest routing protocols and is based on the distance vector model. It uses hop count as its metric, where each router hop is assigned a value of 1. The maximum allowable hop count is 15, limiting RIP to small networks. RIP periodically broadcasts its routing table to neighbors every 30 seconds. The limitations of RIP protocol are: slow convergence. Updates take time to propagate through the network, making RIP unsuitable for larger, dynamic networks. Routing loops. Without mechanisms like split horizon and hold-down timers, routing loops can occur. OSPF operates by constructing a map of the entire network topology using link state advertisements, LSAs. Each router computes the shortest path to every destination using Dijkstra's algorithm. OSPF supports variable length subnet masking, VLSM, and CIDR, making it suitable for large, hierarchical networks. Area design and hierarchical routing. OSPF divides networks into areas to reduce routing table size and improve efficiency. The backbone area, Area 0, connects all other areas, ensuring data can traverse between them. EIGRP is Cisco's proprietary hybrid protocol, combining distance vector and link state features. It uses metrics like bandwidth, delay, load, and reliability to determine the best path. EIGRP's feasible successor mechanism maintains backup routes, enabling fast failover. Though, we have already covered basics of routing for IPv6 in the last lecture, but we will still touch on it in a very summarized way. So, the first protocol we will discuss is RIPNG, the RIP next generation. It is similar to RIP but designed for IPv6. The RIPNG extends RIP to support IPv6 by using 128-bit addresses and multicast for updates. It retains RIP simplicity and hop count metric but operates separately for IPv6. Like RIP, RIPNG uses a maximum hop count of 15, which limits its scalability. The OSPF v3. The OSPF v3 builds upon OSPF for IPv4 but is designed to support IPv6's larger address space and enhanced features. It separates routing processes for IPv4 and IPv6, ensuring efficiency and clarity. In IPv6, OSPF v3 uses link local addresses for router-to-router communication, simplifying neighbor discovery and configuration. The MPBGP known as Multi-Protocol BGP. The MPBGP extends traditional BGP to handle multiple address families, including IPv6. It enables seamless integration of IPv4 and IPv6 routing. MPBGP supports the advertisement of both IPv4 and IPv6 routes within the same protocol, simplifying network management during IPv6 transitions. So, if we talk about IPv4 versus IPv6 protocol capabilities. The IPv4 and IPv6 routing protocols share many core principles but differ due to IPv6's enhancements. The IPv6 routing protocols are designed to handle larger address spaces and better support hierarchical addressing. Protocols like OSPF v3 and MPBGP have been adapted to leverage IPv6's features, such as link local addressing and simplified header structures. Adapting legacy routing protocols for IPv6. Legacy protocols like RIP and OSPF required significant updates to accommodate IPv6. RIPNG added support for IPv6 addressing but retained the simplicity of RIP. OSPF v3 restructured its LSA mechanisms to better suit IPv6's address architecture. Let's now discuss about advanced routing concepts. Routing scalability is essential for managing large and complex networks. Scalability ensures that routing remains efficient and manageable as networks grow in size and complexity. Multi-area OSPF. The open shortest path first supports a hierarchical design by dividing networks into multiple areas. This structure enhances scalability by reducing the size of routing tables and minimizing routing overhead. How multi-area OSPF works. The OSPF's backbone area, Area 0, acts as the central hub connecting all other areas. Non-backbone areas, such as Area 1, Area 2, exchange routing information with Area 0, but not directly with each other. Routers in each area maintain detailed information about their own area but summarize routes when communicating with the backbone, reducing routing table sizes. The advantages of multi-area OSPF are like reduced routing table size. Summarization between areas limits the number of routes shared across the network. Improved performance. By isolating network changes to specific areas, OSPF minimizes the impact of topology changes. Enhanced manageability. Administrators can logically segment networks based on geography, department, or function. The use case may be, a global enterprise network with offices in different regions can use OSPF to create areas for each region, with a backbone connecting them. Let's discuss about the route aggregation and summarization. Route aggregation, also known as summarization, combines multiple routes into a single advertisement. This technique simplifies routing tables and reduces the amount of information shared between routers. How it works. Routes with a common prefix, such as 192.168.00/24, 192.168.1.0/24, are summarized into a single route, such as 192.168.0.0/23. The summarization is typically performed at the boundaries between different network segments or areas. The benefits of route aggregation are reduced overhead. Fewer routes mean less memory and processing power required by routers. Improved stability. Changes in one specific route don't affect the entire network. Scalability. enables large networks to operate efficiently. The challenges are like: the over-summarization can lead to blackholing, where traffic for a non-summarized route is dropped because the summary route doesn't match. Next, we will be discussing about the policy-based routing. It provides greater control over traffic flow by enabling routing decisions based on custom criteria beyond the destination address. Managing traffic using source, destination, and application-based rules. Traditional routing focuses on the destination address to determine the packet's path. PBR allows administrators to consider additional factors, such as source address, route traffic from specific devices or subnets differently. Destination address, prioritize traffic to specific servers or networks. Applications, route specific types of traffic, such as VoIP or video, through higher bandwidth or lower latency paths. The examples of PBR rules are like directing traffic from a VIP client subnet through a high-speed link. Sending bulk backup data through a less expensive, slower link to free up the primary link for time-sensitive traffic. The implementation process includes steps like: the PBR uses access control lists, ACLs, to match packets against criteria and apply routing policies accordingly. The advantage of using PBR are like enhanced control over traffic flow, ability to optimize network resources for specific applications or user groups. The challenges of using PBR are like: it is complex to implement and maintain in large networks. It also requires careful planning to avoid conflicts with dynamic routing protocols. Next, we will be discussing redundancy and load balancing. The redundancy and load balancing are critical for ensuring network reliability and optimizing resource utilization. The failover ensures continuous network operation by redirecting traffic to backup routes or systems when the primary path fails. How failover works. The routers detect link failures using protocols like OSPF, BGP, or HSRP, Hot Standby Router Protocol. Traffic is automatically rerouted to an alternate path. Examples of failover mechanisms are like HSRP or VRRP, provides redundancy for gateway routers, ensuring that one router takes over if the primary fails. BGP path selection, automatically selects the next best route when the preferred path is unavailable. The benefits of failover are: it minimizes downtime in case of failures. It also provides high availability for critical services. The challenges of failover mechanism are like that. It requires redundant hardware and links, which can be expensive. The misconfigured failover setups can lead to routing loops or dropped packets. Let us now discuss about equal cost multipath routing, ECMP. The ECMP is a load balancing technique that allows multiple paths with equal cost to be used simultaneously for forwarding packets. How ECMP works. Routers use hashing algorithms to distribute traffic evenly across available paths. ECMP can split traffic based on source and destination IP, port numbers, or other parameters. The advantages of ECMP are like increased bandwidth utilization. By using multiple paths, ECMP maximizes the available network capacity. Improved redundancy. If one path fails, others can continue to handle traffic without disruption. The limitations of ECMP are: it works best in symmetric topologies where all paths have similar metrics. It may not be effective for applications requiring in-order packet delivery. Let us now understand the basics of route redistribution. The route redistribution allows different routing protocols to share information, enabling interoperability between networks using different protocols. Interoperability between protocols, such as RIP and OSPF. In large networks, multiple routing protocols may coexist due to legacy systems or varying requirements. Redistribution bridges these protocols, allowing routes learned by one protocol to be advertised in another. How redistribution works. The routers configured for redistribution take routes from one protocol's routing table and inject them into another protocol's routing table. For example, routes learned via RIP can be redistributed into OSPF, allowing seamless connectivity between the two domains. The key considerations to be considered while configuring redistribution are like metrics. Protocols use different metrics, such as RIP uses hop count, while OSPF uses cost. During redistribution, appropriate metric values must be assigned. Route filtering. Administrators can filter which routes are redistributed to prevent unnecessary or undesirable routes from propagating. Benefits of redistribution are: the redistribution ensures smooth communication between networks running different protocols, and it facilitates gradual migration from one protocol to another. The challenge in redistribution are that it can lead to routing loops or suboptimal paths if not carefully configured. It adds complexity to network management. In this section we have looked into advanced routing concepts that ensure networks are scalable, efficient, and reliable. Routing scalability focuses on optimizing OSPF and using summarization to manage large networks effectively. Policy-based routing offers granular control, enabling routing decisions tailored to specific traffic needs. Redundancy and load balancing enhance network reliability and resource utilization through failover mechanisms and ECMP. Route redistribution ensures interoperability between protocols, allowing diverse systems to coexist seamlessly. Mastering these concepts equips network professionals to design robust, high-performance networks capable of meeting modern demands. Next, we will be discussing about routing in modern networks. Modern networks demand dynamic, flexible, and efficient routing solutions to address the complexities of software-defined infrastructures, cloud environments, and mobile networks. This module explores these advanced routing paradigms such as software-defined networking, SDN. In traditional networks, routing decisions are distributed across routers, each making independent decisions based on its routing table. Software-defined networking transforms this model by centralizing routing and traffic management. Role of SDN controllers. The SDN separates the control plane, decision-making, from the data plane, packet forwarding. A centralized controller manages the entire network and provides a global view of network topology. Routing rules are defined at the controller and dynamically pushed to switches and routers, allowing consistent and optimized traffic flow. Benefits of centralized management are: simplified network management. Administrators can configure and update routes for the entire network from a single point. Faster adaptation. Centralized control enables rapid response to changes in network conditions, such as congestion or link failures. Programmability. Administrators can automate routing tasks and create customized traffic policies using APIs provided by SDN controllers, such as OpenDaylight or ONOS. Dynamic route adjustments with OpenFlow. In any SDN network, the OpenFlow is a key protocol that enables SDN controllers to communicate with switches and routers. It defines how routing rules are installed, modified, and deleted. How OpenFlow works. The controller uses OpenFlow to install flow entries in switches, specifying actions for packets matching certain criteria, such as source/destination IP, port numbers. These rules dictate how traffic is forwarded, mirrored, or dropped. Dynamic adjustments. The SDN controllers monitor network conditions in real time, such as link utilization and packet loss. Based on these metrics, they dynamically adjust routing rules to optimize performance, balance load, or reroute traffic during outages. The sample use case may be that in a data center, OpenFlow can dynamically reroute traffic away from congested links, ensuring consistent application performance. Next, we will be discussing about the cloud-based routing. As organizations increasingly adopt cloud solutions, routing in cloud environments has become a critical aspect of network design. Cloud providers often use overlay networks to simplify routing in multi-tenant environments. These overlays abstract the underlying physical network, creating logical network topologies. The virtual networking technologies like VXLAN, Virtual Extensible LAN, and GRE, Generic Routing Encapsulation, are used to encapsulate traffic between virtual machines or containers. Overlays enable tenants to create isolated networks, regardless of the physical infrastructure. The benefits of overlay networks are: scalability. Overlay networks can accommodate thousands of virtual networks without changes to the physical infrastructure. Flexibility. Organizations can build complex topologies, such as multi-tier applications, across geographically distributed data centers. Security. Traffic is isolated between tenants, preventing unauthorized access. The challenges of overlay network are like: overlay networks introduce encapsulation overhead, which can impact performance. Troubleshooting is more complex because of the additional abstraction layer. Next, we will discuss about the role of BGP in hybrid and multi-cloud environments. Border Gateway Protocol is integral to routing in hybrid and multi-cloud setups, where workloads span on-premises, data centers, and multiple cloud providers. So, how BGP supports cloud routing? BGP enables connectivity between different autonomous systems, such as a company's on-premises network and its cloud provider. BGP advertises prefixes for workloads hosted in cloud environments, ensuring seamless connectivity. The use cases in cloud environments. Hybrid cloud, BGP routes traffic between on-premises applications and cloud-based services. Multi-cloud, organizations use BGP to interconnect workloads across multiple cloud providers, such as AWS, Azure, Google Cloud. The advantages of BGP in cloud are: scalability. BGP can handle large-scale networks with numerous prefixes. Policy control. BGP policies allow organizations to prioritize specific routes or control traffic flow between clouds. The challenges of using BGP in cloud are like: configuring and optimizing BGP in hybrid or multi-cloud environments requires expertise. The BGP convergence times may impact performance during route changes. Let us now discuss about the routing in ad hoc and mobile networks. In scenarios where infrastructure is limited or constantly changing, such as disaster zones or vehicular networks, traditional routing protocols are insufficient. Ad hoc and mobile networks address these challenges. The challenges in MANET and VANET routing are like: MANET, Mobile Ad Hoc Network. A MANET is a self-configuring network of mobile devices that communicate directly without fixed infrastructure. The challenges are like: dynamic topology, nodes frequently join, leave, or move, making routing highly volatile. Limited resources, MANETs often operate on devices with constrained battery, processing power, and bandwidth. Scalability issues. As the number of nodes increases, routing complexity grows. The VANETs enable communication between vehicles, V2V, and with roadside infrastructure, V2I. The challenges are like: high mobility, vehicles move quickly, causing rapid topology changes. Real-time requirements, applications like collision avoidance demand low-latency communication. Interference. Urban environments introduce obstacles that disrupt wireless signals. The protocols for MANETs are: AODV, Ad Hoc On-Demand Distance Vector. It is a reactive protocol that creates routes only when needed. Reduces overhead by avoiding periodic updates. The DSR, Dynamic Source Routing. It uses source routing, where the entire path is included in the packet header. Suitable for small to medium-sized networks. Next, the protocols for VANETs are: GPSR, Greedy Perimeter Stateless Routing. It uses geographic information to forward packets. It is effective in highly dynamic vehicular environments. CR, Connection-Aware Routing. It prioritizes routes with stable connections, minimizing packet loss due to frequent disconnections. The hybrid approaches combine reactive and proactive routing methods for better adaptability in dynamic scenarios. In summary, the SDN revolutionizes routing by centralizing management and enabling dynamic adjustments through protocols like OpenFlow. The cloud-based routing leverages overlay networks and BGP to provide scalable, secure, and flexible connectivity for hybrid and multi-cloud environments. The ad hoc and mobile networks introduce specialized protocols like AODV and GPSR to handle the dynamic and resource-constrained nature of MANETs and VANETs. By understanding these advanced concepts, network engineers can design resilient, efficient, and future-proof networks that meet the demands of today's complex environments. Routing security is critical in modern networks as attackers increasingly target routing protocols to disrupt communication, hijack traffic, or compromise data integrity. This module explores the challenges, best practices, and advanced techniques to secure network routing. Routing security challenges are like routing table poisoning and hijacking. Routing table poisoning and hijacking are significant threats that can compromise the integrity and functionality of network routing. Routing table poisoning. In this attack, malicious or false routing information is injected into a router's routing table. This can cause packets to take inefficient or insecure routes, get dropped or loop indefinitely. For example, an attacker could broadcast incorrect RIP updates to neighboring routers, disrupting normal traffic flow. Routing hijacking. In a hijacking attack, an attacker advertises itself as the best route to a specific destination, redirecting traffic through its system. This enables activities such as eavesdropping, monitoring sensitive data, man-in-the-middle attacks, modifying or injecting malicious data into legitimate communications. For example, in 2018, a large-scale BGP hijacking attack rerouted internet traffic through malicious servers, exposing sensitive information. The best practice to secure routing are like MD5 authentication for OSPF and RIP. Routing protocols like OSPF and RIP were not originally designed with robust security measures, making them vulnerable to spoofing and injection attacks. Adding MD5 authentication enhances their security. How MD5 authentication works. The MD5 is a cryptographic hash function that generates a fixed-size hash value from a message. In OSPF and RIP, MD5 authentication ensures that only routers with the correct authentication key can exchange routing information. Configuration in OSPF. The OSPF supports MD5 authentication for securing hello and routing update messages. An MD5 hash of the message and a shared key is appended to packets. The receiving router validates the hash before accepting the message. Configuration in RIP. RIP uses MD5 to authenticate RIP updates, preventing unauthorized devices from injecting malicious routes. The benefits of using authentication in RIP or OSPF are that it protects against spoofing and unauthorized updates, and it enhances the trust between routers. BGP security enhancements. BGP is vital for Internet routing, but its lack of built-in security mechanisms makes it susceptible to attacks such as hijacking and spoofing. Some of the techniques we use are route filtering. The filters are applied to control the prefixes advertised or accepted by BGP neighbors. For example, blocking prefixes not belonging to a legitimate AS. Preventing advertisements of overly specific prefixes, also known as prefix deaggregation. TTL security mechanism, GTSM. BGP uses time-to-live values to ensure that BGP packets originate from directly connected peers, preventing spoofed packets from distant attackers. RPKI, the Resource Public Key Infrastructure. RPKI is a cryptographic method for verifying the ownership of IP prefixes. It helps prevent BGP hijacking by ensuring that only authorized ASs can advertise specific prefixes. The advanced threat mitigation techniques can also be used like Secure BGP. The Secure BGP is an enhancement to traditional BGP designed to address its security vulnerabilities. The key features of SBGP are: digital signatures, ensures the authenticity of routing announcements. Route attestations, routers cryptographically sign route advertisements to prove their legitimacy. Public key infrastructure, PKI SBGP uses PKI to distribute and validate digital certificates for ASs. The benefits of SBGP: it prevents unauthorized route advertisements. Also ensures that traffic is routed through legitimate AS paths. The challenges of SBGP are: the SBGP introduces significant computational overhead for signing and verifying route announcements. And the deployment requires widespread adoption, which has been slow till the date. Next, we will discuss about detecting and addressing routing attacks. Detecting and mitigating routing attacks is essential for maintaining network integrity. Some of the strategies include monitoring and logging. Tools like Wireshark and SNMP-based monitoring systems can detect unusual routing behavior or unauthorized route updates. Anomaly detection. Use machine learning algorithms to identify abnormal patterns in routing advertisements or traffic flows. For example, sudden changes in route paths or spikes in updates could indicate a hijacking attempt. Route validation. Implement route validation mechanisms like RPKI or BGSec to ensure the authenticity of routing information. Incident response. Create and regularly test incident response plans for routing-related attacks. For example, quickly withdraw malicious route advertisements and re-advertise legitimate ones in the event of a hijacking. Routing security is a critical component of modern networking. From addressing challenges like routing table poisoning and route flapping to implementing secure practices such as MD5 authentication and BGP security enhancements, organizations must adopt robust strategies to protect their networks. Advanced solutions like secure BGP and proactive monitoring further mitigate threats, ensuring routing integrity in increasingly complex environments. By mastering these practices, network engineers can safeguard critical infrastructure against evolving threats. With this we come to end of this lecture. In this session, we delved into advanced routing concepts essential for building scalable and efficient networks. Here's a quick recap of the key takeaways. Multi-area OSPF explored how OSPF's hierarchical design enhances scalability and reduces routing overhead. Route aggregation and summarization, learned how combining routes optimizes routing tables and improves network stability. Policy-based routing, PBR, understood how PBR allows granular control by routing traffic based on source, destination, or application. Redundancy and load balancing, discussed failover mechanisms and equal-cost multipath routing, ECMP, for network reliability. Route redistribution, examined how to enable interoperability between different routing protocols like RIP and OSPF. In the next lecture, we'll move into the practical hands-on as we explore lab setups and network configurations for ethical hacking. This is where we start getting practical hands-on with configuring virtual labs for simulating real-world network environments, setting up tools and frameworks used in penetration testing, building a strong foundation for testing vulnerabilities and securing networks effectively. This will be an exciting transition from theory to practice, so be ready to roll up your sleeves and get your hands dirty with ethical hacking. If you found this lecture helpful, please like, share, and subscribe to the AI Academy. Don't forget to hit the notification bell so you never miss an update. Your support keeps us motivated to bring you more valuable content. See you in the next session.